Welcome to the explainer. It's a pretty wild stat, but once a network perimeter is breached, over 70% of lateral network traffic goes completely unmonitored. If you're a cloud architect, a DBA, or an IT ops, you already know that security is absolutely not an afterthought anymore. It's literally the foundation of everything we build. So today we're diving straight into a highly critical, yet honestly sometimes kind of misunderstood topic, configuring network encryption for your Oracle databases using SSL and TLS 1.2. We're going to synthesize the architecture, break down the key concepts, and give you the exact practical takeaways you need to lock down your environments. Let's get into it. All right, let's just quickly glance at our roadmap for today. We're going to hit 1. The encryption imperative, 2. Oracle SSL TLS architecture, 3. One-way versus two-way TLS, 4. Certificate chains, and 5. Implementation steps.
Okay, part 1, the encryption imperative.
So here's the fundamental issue, right? Data in transit is incredibly vulnerable. Why? Well, think about legacy systems. A lot of them were built assuming the internal network was this perfectly safe walled garden, transmitting highly sensitive data in completely unencrypted plain text. If bad actors manage to get inside your network, that data in motion is essentially just handed over to them on a silver platter.
And this glaring vulnerability is exactly why network encryption is, well, it's just not optional anymore. The massive industry shift toward cloud transformation means our data is traversing much broader, way more complex networks. Plus, strict compliance standards like HIPAA for healthcare or PCI DSS for payment cards are really forcing our hands here. If you're handling credit card numbers or patient records, having a robust encryption between the client and the database is a hard, non-negotiable mandate.
Moving right along to Section 2, Oracle SSL/TLS architecture.
Now, if you're managing a mixed version environment, and let's be honest, a lot of us are, context is everything here. Notice that if you're still running 11G, getting up to a modern standard like TLS 1.1 or 1.2 actually requires applying specific MES bundle patches. 12C supports it natively, and by the time you get to 19C, our absolute focus should be totally locked on TLS 1.2 to ensure maximum security across the board. To actually make all this work, we've got to define the Oracle Wallet first. This is absolutely foundational. Think of the Oracle Wallet as this highly secure, actually think of it as a specialized vault where your database actively stores its SSL certificates and the cryptographic keys it needs to build that encrypted channel. It's basically the central nervous system of your database's identity. Building right on top of that, the cryptographic engine Oracle relies on is PKI, or Public Key Infrastructure. Here's how it flows. When a certificate request is generated in your wallet, a private key is created, while a public key is provided with the signed certificate. Oracle then uses third-party PKI libraries to encrypt data with the public key and decrypt it with the private key, successfully negotiating that secure handshake over the network. All right, Section 3, one-way versus two-way TLS. It's really easy to just assume that two-way TLS, often called mutual TLS or MTLS, is always the right answer, simply because it forces both sides to prove their identity. But in a one-way TLS setup, the server deliberately skips validating the client. It only shares its public certificate so the client can verify it's talking to the real database. So you might be wondering, why would we ever choose the supposedly less secure one-way option? Well, here's the real kicker. One-way TLS actually offers some massive operational benefits. Because the client doesn't need to share a certificate, you completely eliminate the need to manage or download client-side wallets, which saves you from a colossal administrative headache. In fact, starting from Oracle Client 19.14, public certs are built right in. It also cuts down the handshake round trip, which means reduced connection latency. You can leverage the OS default trust store, and incredibly, it can happily coexist on the exact same server right alongside a stricter two-way TLS setup. Next up, Section 4, Understanding Certificate Chains. Okay, so a certificate chain is essentially just an ordered list of vouchers. Right at the very top, you have your root CA certificate. This is the ultimate anchor of trust that terminates your entire chain. It is always securely self-signed by the certificate authority itself. Every single signature down the line has to be successfully verified all the way back up to this specific root certificate. But here is where so many IT admins get totally tripped up, the intermediate certificate. This is a subordinate certificate sitting directly between your database's SSL certificate and that root CA. It acts as the direct issuer.
If you fail to install this middleman on your server, you will break compatibility, and various browsers, apps, and client machines simply won't trust your database connection. Seriously, whatever you do, do not forget the intermediate.
Finally, Section 5, Implementation and Configuration. Okay, let's talk execution. For internal testing or your lower environments, going the self-signed route is excellent. It's very hands-on. You build your Oracle wallets using tools like Aura PKI, generate self-signed certificates right inside them, securely copy them across the network using SCP, and then manually import the client cert to the server and vice versa. Now, option 2 is what you're going to use for enterprise production. Instead of self-signing, you create a wallet and generate a certificate signing request, or CSR. You take that CSR and submit it to your corporate or third-party certificate authority. When they send the signed certificates back, you have to meticulously import the entire chain of trust. So that's the root, the intermediate, and finally your user certificate straight back into your Oracle wallet.
Regardless of which path you choose, the real magic happens in 3 core config files. You update sqlnet.aura on both sides so it points to your new wallet directory. You configure listener.aura on the server so it listens on a new SSL/TLS port. And critically, this is the big one, on the client side in tnsnames.aura, you change your connection string protocol from standard TCP over to TCP/S, which stands for TCP Secure. Once you do that, your session tunnels safely through encrypted TLS 1.2. All right, I want to leave you with a bit of a provocative question to take back to your team today. We've seen how to architect this, how the keys are exchanged, and the exact steps to roll it out. But the real work, that starts with an audit. Are your legacy database systems secretly relying on unencrypted plaintext connections right now? It's time to check those endpoints, review those configurations, and close those plaintext gaps today. Thanks for joining me on this explainer, and I'll catch you in the next one.